In the vast expanse of our cosmos, a delicate ballet unfolds. Stars burn with steady flames, planets trace perfect ellipses around their suns, and light streams across the universe at precisely 299,792,000 meters per second. Not faster, not slower, always exactly the same, whether measured in a laboratory on Earth or observed in the light from galaxies billions of light years distant. These constants of nature, these physical laws, are the silent architects of everything we see, touch, and experience. They are the invisible scaffolding upon which reality itself is constructed. Like ancient foundations beneath a magnificent cathedral, we rarely notice them, yet they support everything we know. The speed of light, the gravitational constant, Planck's constant, the charge of an electron, the fine structure constant, the mass of a proton, each one precisely tuned, each one apparently unchanging since the birth of our universe nearly 14 billion years ago. These numbers don't merely describe our universe, they define it. They constrain what can happen and what cannot. They determine how atoms form, how stars shine, how gravity pulls, and ultimately, how life itself emerges. When you look up at the night sky, you witness the product of these constants. The steady fusion in stellar cores depends on the exact strength of the nuclear forces. The orbital dance of planets relies on the precise value of the gravitational constant. The very light that reaches your eyes travels at its unvarying speed across the cosmic void. Even the atoms that make up your body exist only because these constants allow electrons to bind to nuclei in stable configurations. For centuries, scientists have measured these constants with increasing precision, finding them unwavering, eternal, fixed. In laboratories across continents and centuries, the same experiments yield identical results. The same physical laws that govern a falling apple on Earth appear to govern distant galaxies and ancient light that began its journey when our planet was young. This constancy gives us comfort. It suggests a universe of order and predictability, a cosmos we can understand through careful observation and mathematical modeling. But what if this constancy is an illusion? What if the laws of physics aren't truly constant at all? It sounds almost heretical to suggest. Our entire scientific enterprise rests upon the assumption that natural laws remain unchanged across time and space. The mathematics we use to model reality assumes these numbers stay fixed. Our technology depends on their reliability. Our very existence seems predicated on their stability. Yet the question persists, whispering from the edges of our knowledge. What if the speed of light was different a billion years ago? What if gravity grows imperceptibly stronger with each passing millennium? What if the fine structure constant, which determines how strongly atoms hold onto their electrons, varies across the vast reaches of space? Or more dramatically, what if these constants could suddenly shift, like a cosmic earthquake, rewriting the rules of reality in an instant? The implications would be profound, stretching far beyond abstract physics to challenge our very understanding of existence. Stars might flicker out or explode. Chemistry could change, rendering familiar substances strange and unpredictable. The delicate balance that allows complex structures to form might be disrupted. Life itself might become impossible in a universe with altered rules. This is not merely an academic thought experiment. Some researchers have found tantalizing hints that certain constants might actually vary across the vast reaches of space or the deep abyss of time. Others explore theoretical frameworks where changes in physical law are not just possible, but inevitable. The constants we rely upon might be variables in disguise, changing so slowly that we mistake them for fixed values in our brief moment of cosmic observation. In distant quasars, astronomers have detected possible variations in the fine structure constant. In the cosmic microwave background, that ancient light from the early universe, physicists search for signs that fundamental constants might have been different in the distant past. In theoretical physics, some models suggest our universe might be just one bubble in a vast multiverse, each realm governed by its own unique set of physical laws. As we drift through our seemingly stable cosmos, wrapped in the comfortable predictability of unchanging natural law, we must ask ourselves, how permanent are the laws that govern everything? Are they truly written in stone, or might they be scribbled in sand, vulnerable to the tides of cosmic change? In this journey together, we will explore what happens when we question one of our most fundamental assumptions about reality. What happens if the laws of physics just change? We'll venture into strange new territories of thought, where gravity might strengthen or weaken, where light might speed up or slow down, where the very building blocks of matter might behave according to different rules. We'll consider how the cosmos might reshape itself under altered laws, and what such changes would mean for stars, planets, and living things. The universe we know might be more precarious than we imagine, balanced on a knife edge of physical constants. And perhaps, in contemplating its fragility, we might better appreciate the remarkable cosmic coincidence that allows us to exist at all, in this moment, under these particular laws, which have remained stable long enough for stars to form, planets to cool, and consciousness to arise and wonder at it all. What exactly are physical laws? We speak of them with such certainty, these foundational principles upon which we build our understanding of the cosmos. Yet defining them precisely proves surprisingly elusive. Are they discoveries or inventions? Are they properties of nature itself, or merely human approximations? Are they eternal truths or temporary patterns? In their simplest form, physical laws are statements that describe regularities in natural phenomena. They tell us how objects move when forces act upon them, how energy transforms but never disappears, how particles interact across empty space. These descriptions often take mathematical form, equations that predict with astonishing accuracy how systems will behave. Consider Newton's law of universal gravitation. Two masses attract each other with a force proportional to their masses and inversely proportional to the square of the distance between them. Simple, elegant, powerful. With this single equation, we can track the motion of falling apples and orbiting planets alike. For over 2 centuries, this law seemed absolute, a perfect description of gravity's action throughout the cosmos, until it wasn't. Einstein's general relativity revealed that Newton's law was merely an approximation, accurate enough for most everyday purposes, but fundamentally incomplete. Gravity, Einstein showed us, isn't a force at all, but the curvature of space-time itself. The universe had revealed another layer of its mysteries. This pattern has repeated throughout the history of science. What we once considered inviolable laws often turn out to be special cases of deeper principles. Our current laws, impressive as they are, may similarly be approximations of truths we have yet to discover. The journey to uncover these principles stretches back to ancient civilizations. The Babylonians tracked celestial motions with mathematical precision. The Greeks sought geometric harmony in nature. But it was during the scientific revolution of the 16th and 17th centuries that our modern concept of physical laws truly emerged. Galileo Galilei, watching a lamp swing in the Cathedral of Pisa, discovered that a pendulum's period depends only on its length, not the weight of the bob or the width of its swing. By timing pulses with his own heartbeat, he uncovered a mathematical regularity in what had previously seemed merely commonplace. Isaac Newton, building on Galileo's insights, formulated laws of motion that applied equally to terrestrial and celestial objects, unifying what had long been considered separate realms. His laws of motion and universal gravitation suggested a clockwork universe, deterministic and predictable. In the centuries that followed, scientists discovered constants that seemed to govern the behavior of heat, light, electricity, and magnetism. The number pi appears in formulations of gravity, electromagnetism, quantum mechanics, and cosmology. The speed of light, represented by c, stands as an upper limit for all matter and information. Planck's constant, h, governs the strange behavior of the quantum realm. These constants seem woven into the fabric of reality itself. Measure them wherever you wish, whenever you wish, and they remain the same. The speed of light is identical whether measured in a laboratory in Tokyo or inferred from observations of distant galaxies. The charge of an electron in a modern particle accelerator matches that in stars born billions of years ago. This universality gives physical laws their power. A law that works only sometimes, or only in certain places, isn't a law at all, merely a curiosity. True physical laws apply everywhere and everywhen, at least within the domain where they have validity. But how do we know these laws are truly universal? Our direct observations are limited to an infinitesimal fraction of the universe, both in space and time. We assume that what we observe locally holds true throughout the cosmos, but this is ultimately an assumption, albeit one supported by all available evidence. The laws themselves exist in a hierarchy. At the foundation lie the fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. These appear irreducible, not derivable from anything deeper, though physicists search for a grand unified theory that might reveal connections among them. From these fundamental forces emerge the laws of classical mechanics, thermodynamics, and optics, which in turn give rise to the principles governing chemistry, biology, and eventually, perhaps, even consciousness itself. The complexity of the universe unfolds from simple beginnings, like an elaborate symphony developing from a few basic themes. Physical laws are often expressed as mathematical constraints. Conservation laws tell us what cannot change in physical processes. Energy can neither be created nor destroyed, merely transformed. The total electric charge in a closed system remains constant. Angular momentum persists unless external torques act upon a system. These constraints shape the cosmos. Stars burn for billions of years because nuclear fusion releases energy gradually, not all at once. Planets orbit in stable patterns because angular momentum preserves their motion. Atoms remain stable because electrons can only occupy certain energy levels, not any arbitrary state. The laws governing these constraints appear finely tuned. Change the strength of gravity by a tiny fraction, and stars couldn't form. Alter the balance between electromagnetic and nuclear forces, and atoms themselves might become impossible. Our universe seems balanced on a knife edge of possibility, with physical laws precisely calibrated to allow complexity to emerge. This apparent fine-tuning has led some to invoke the anthropic principle, the idea that we observe these particular physical laws precisely because they allow observers like us to exist. In a multiverse of many possible physical law configurations, we necessarily find ourselves in one of the rare universes where physical laws permit the complexity required for life. Others see in this fine-tuning evidence of purpose or design a universe calibrated specifically to allow consciousness to develop and contemplate its own origins. Still, others search for deeper principles that might explain why physical laws take the particular values they do, suggesting that what appears arbitrary might actually be necessary. The laws of physics also determine how energy flows through systems. The second law of thermodynamics tells us that entropy, a measure of disorder, tends to increase over time. This introduces an arrow of time into the universe, distinguishing past from future in a way that other physical laws do not. Heat flows from hot to cold, never the reverse. A dropped egg shatters, but the pieces never spontaneously reassemble themselves. These everyday observations reflect the inexorable increase of cosmic entropy, the universe's slow march from the exquisite order of the Big Bang toward an eventual heat death, where all energy has dispersed into uniform, featureless warmth. Yet within this overall trend toward disorder, local pockets of increasing complexity can emerge. Living organisms maintain internal order by increasing entropy elsewhere. Stars forge complex elements from simple hydrogen. Conscious minds create elaborate structures of knowledge and meaning. These islands of complexity rely upon the consistent operation of physical laws to maintain their intricate organization. Whether these laws are absolute or contingent remains one of the deepest questions in physics. Do they represent necessary truths that couldn't possibly be otherwise? Or are they accidents of cosmic history, the particular configuration our universe happened to adopt, while other universes might operate according to entirely different principles? The constants that appear in our physical laws, from the gravitational constant g to the fine structure constant alpha, seem arbitrary. No theory yet tells us why they take their particular values. They must be measured through observation, rather than derived from first principles. This suggests contingency, rather than necessity, values that happen to emerge, rather than ones that had to be. Some theoretical frameworks, like string theory, suggest that what we perceive as fundamental constants might actually be the result of how extra dimensions are compactified, or how fields settle into their vacuum states. What seems like an arbitrary constant in our four-dimensional space-time might reflect the geometry of hidden dimensions beyond our direct perception. What's perhaps most remarkable about physical laws is not just that they exist, but that we can comprehend them. The human mind, itself a product of the very laws it studies, has proven capable of discerning the patterns governing reality. As physicist Eugene Wigner noted, this unreasonable effectiveness of mathematics in describing the natural world constitutes a profound mystery in itself. Our understanding of physical laws continues to evolve. Quantum mechanics revealed a probabilistic underpinning to what had seemed deterministic rules. General relativity showed that space and time themselves are dynamic participants in physical processes, not just the stage upon which they unfold. Each revolution in physics doesn't merely add detail to our picture of reality, but fundamentally transforms how we conceptualize the universe and its governing principles. And so we arrive at our central question: are these laws truly constant? Do they remain unchanged across the vast distances and times our universe encompasses? Or might they themselves be subject to evolution and change, varying across cosmic reaches or transforming over eons? The answer to this question would reshape not just physics, but our entire conception of reality itself. For a universe with changing laws is a far stranger place than the one we thought we knew, a realm where prediction falters and certainty dissolves into shifting sands of possibility. For most of scientific history, the constants of nature were assumed to be exactly that constant. Unchanging values woven into the fabric of reality itself. But in recent decades, a subtle yet profound question has emerged in the halls of physics departments and beneath the domes of observatories around the world. What if these constants aren't truly constant after all? The idea isn't as radical as it might first appear. Our universe has already shown itself to be far stranger than our ancestors imagined. Space and time curve and stretch. Particles exist in multiple states simultaneously until measured. Empty space seethes with virtual particles popping in and out of existence. Perhaps constancy itself is merely another illusion, a product of our limited perspective. The quest to detect changing constants represents one of modern physics' most challenging frontiers. Any variations would likely be extremely subtle. After all, if physical constants varied wildly or rapidly, the universe as we know it simply couldn't exist. Stars would flicker out, atoms would disintegrate. The delicate dance of forces that allows complexity to emerge would collapse into chaos. Instead, physicists search for minute shifts, tiny variations that might accumulate over vast distances or enormous spans of time. They peer back billions of years by studying light from distant quasars, seeking evidence that the fundamental rules governing atomic behavior might have been slightly different in the cosmic past. One of the most intensely studied potential variables is the fine structure constant, often represented by the Greek letter alpha. This dimensionless number, approximately 1/137, governs the strength of the electromagnetic force. It determines how strongly electrons bind to atomic nuclei, how atoms form molecules, and how light interacts with matter. If alpha were significantly different, chemistry as we know it would be impossible. Stable atoms couldn't form, or would take radically different configurations. The periodic table of elements would be unrecognizable. And since chemistry underlies biology, life itself might never have emerged in a universe with a substantially different fine structure constant. In 1999, a team of astronomers led by John Webb began analyzing light from distant quasars that had passed through intervening gas clouds. When light passes through such clouds, atoms in the gas absorb specific wavelengths, creating dark lines in the resulting spectrum. The exact positioning of these absorption lines depends on the value of the fine structure constant. What Webb and his colleagues found was startling. Their analysis suggested that the fine structure constant might have been slightly different billions of years ago, smaller by about 1 part in 100,000. If confirmed, this would be revolutionary evidence that the laws of physics themselves have changed over cosmic time. Other researchers soon joined the hunt, using different telescopes and methodologies to test this extraordinary claim. Some found results consistent with Webb's findings. Others found no evidence of variation. Still others found hints of change, but in the opposite direction, suggesting alpha might have been larger rather than smaller in the distant past. The debate continues to this day with no clear consensus. The potential variations, if they exist at all, lie at the very edge of our observational capabilities. Systematic errors in measurement and analysis could potentially explain the apparent changes. Yet the possibility remains tantalizing. More recently, some researchers have suggested that the fine structure constant might vary, not just over time, but over space as well. Webb's team has presented evidence suggesting alpha might be slightly different in different directions of the cosmos, creating a kind of dipole across the observable universe. If true, this would be even more surprising than a simple time variation, potentially suggesting our universe has a preferred direction or axis. The fine structure constant isn't the only physical constant under scrutiny. Physicists have also searched for variations in the ratio of the electron mass to the proton mass, the strength of the strong nuclear force, and even the speed of light itself. The cosmic microwave background, that faint afterglow of the Big Bang permeating all of space, provides another window into possible variations. This ancient light shows us the state of the universe when it was only about 380,000 years old. Subtle patterns in its temperature and polarization could potentially reveal changes in fundamental constants between that early epoch and today. So far, analysis of the cosmic microwave background hasn't revealed definitive evidence of changing constants, but it does set strict limits on how much they could have varied. Any changes must be extremely small, constrained to less than about 1 part in a million for most physical constants. Laboratory experiments offer another approach to detecting potential variations. By comparing different types of atomic clocks over years or decades, physicists can place incredibly tight constraints on present-day changes in fundamental constants. The most precise of these experiments can detect changes as small as 1 part in 10 to the 18th power per year, an astonishing level of sensitivity. These laboratory measurements consistently show no evidence of changing constants in the current epoch. If the fundamental constants are changing, they're doing so at a rate too slow for even our most sensitive instruments to detect directly. Yet cosmic history offers plenty of time for even imperceptibly slow changes to accumulate into significant shifts. The universe is nearly 14 billion years old. A change too small to measure over a human lifetime could still produce substantial variations over geological or astronomical timescales. Natural nuclear reactors provide another intriguing line of evidence. Approximately 2 billion years ago, in what is now Gabon in Western Africa, concentrations of uranium-rich ore became naturally critical, sustaining nuclear fission reactions for hundreds of thousands of years. By analyzing the isotopic composition of these ancient reactor sites, physicists can infer the values of certain fundamental constants at that time. Studies of these natural reactors in Oklo, Gabon, have yielded mixed results. Some analyses suggest potential variations in the fine structure constant or the ratio of electron to proton mass, while others find consistency with present-day values. The evidence remains inconclusive, but the mere existence of such natural experiments extends our ability to probe potential variations across deep time. The search continues in other domains as well. Geologists examine ancient mineral deposits for signs of altered radioactive decay rates that might indicate changing constants. Paleontologists study fossils for evidence of different gravitational conditions. Astronomers analyze the light from stellar explosions billions of light years away, seeking subtle anomalies that could reveal a shifting fundamental framework. Theoretical physics also offers frameworks where changing constants might naturally arise. In some models of the early universe, fundamental constants could have settled to their current values during phase transitions as the cosmos expanded and cooled. These models suggest constants might still be slowly evolving, seeking their final equilibrium values. The string theory landscape, with its vision of a multiverse containing perhaps 10 to the 500th power different possible universes, each with its own set of physical laws, provides another context for varying constants. In some versions of string theory, what we perceive as fundamental constants might actually be fields that can vary across space and time. One particularly speculative idea involves hypothetical particles called dilatons, or moduli, predicted by some versions of string theory. These particles could be responsible for setting the values of certain constants. If they aren't completely stabilized, their slow drift could cause corresponding changes in physical constants across cosmic history. If physical constants do change, the variations would likely follow patterns dictated by deeper principles. Conservation laws and symmetries might constrain how constants can vary relative to one another. The total energy of a closed system must remain constant, even if the constants governing individual interactions within that system drift over time. This raises profound questions about the nature of physical law itself. If constants can change, are they really constants at all? Or are they merely parameters in a more fundamental theory, variables whose specific values reflect cosmic history rather than immutable necessity? Perhaps what we call constants are actually the current values of fields that permeate the universe. These fields might have settled into nearly stable configurations in our present cosmic epoch, creating the illusion of fixed constants over the relatively brief span of human observation. This view aligns with a broader conception of cosmic evolution, where the universe itself develops and changes, not just in its contents, but in its fundamental character. The laws we observe might represent a mature phase of an evolving cosmos, with different principles governing earlier epochs or distant regions. If this perspective proves correct, it would dramatically transform our understanding of reality. The universe would not be a static stage governed by unchanging rules, but a dynamic entity whose very laws participate in its ongoing evolution. Constants would have histories, equations would have biographies. The evidence for such a dramatic revision remains tentative at best. Most observations continue to support the traditional view of immutable physical law. The constants we measure today appear identical to those inferred from light that has traveled across billions of light years and billions of years. Yet the question persists, driving innovation in observation and theory alike. New telescopes scan the skies with unprecedented precision. Novel laboratory techniques push the boundaries of measurement to ever more extreme limits. Theoretical physicists develop mathematical frameworks that might explain why constants take the values they do, and whether those values might change. The search for varying constants represents science at its most profound, questioning not just our specific models of reality, but the very nature of physical law itself. It pushes our observational capabilities to their limits and challenges our most fundamental assumptions. For now, the constants of nature continue to appear constant, at least within the precision of our measurements. But the possibility of cosmic evolution at the deepest level remains open, a tantalizing frontier at the edge of human knowledge. In the vastness of space and the depths of time, the unchanging might yet prove changeable, revealing new layers of order in our extraordinary universe. Gravity. The most familiar yet perhaps the most mysterious of the fundamental forces. It shapes our everyday experience, keeping our feet firmly planted on the ground. At cosmic scales, it architects the universe itself, sculpting galaxies, birthing stars, and orchestrating the dance of planets around their suns. What would happen if this most constant companion suddenly changed its nature? If the gravitational constant, that number denoted by the letter G in physics equations, were to shift its value, the implications would cascade through every level of cosmic structure, from the largest superclusters of galaxies down to the orbit of electrons around atomic nuclei. Let us first understand what gravity truly is. According to Einstein's general relativity, gravity isn't really a force at all, but the curvature of space-time caused by mass and energy. Massive objects like stars and planets create indentations in the fabric of space-time, rather like heavy balls placed on a stretched rubber sheet. Other objects follow the curves created by this warping as they move through space. The strength of this curvature is governed by the gravitational constant, G, which has the measured value of approximately 6.67 times 10 to the negative 11 cubic meters per kilogram per second squared. This seemingly arbitrary number has remained unchanged, as far as we can tell, throughout the observable universe and across cosmic history. But what if G were different? What if the relationship between mass and space-time curvature suddenly shifted? Let's imagine gravity becoming stronger. Perhaps G doubles in value overnight. The effects would be immediate and catastrophic. Your body weight would instantly double, potentially causing your legs to buckle beneath you. Buildings designed for normal gravitational conditions would face enormous stress, with many modern structures collapsing under their own newly doubled weight. The oceans would be pulled more strongly toward Earth's center, causing sea levels to drop at the coasts while water depth increases in the middle of the oceans. Tidal forces would strengthen, generating massive tsunamis that would devastate coastal regions worldwide. But these terrestrial effects, dramatic as they are, pale beside the cosmic consequences. Our planet's orbit around the Sun would begin to decay. Earth would spiral inward, growing hotter as it approached our star. Without intervention, we would eventually plunge into the Sun itself, though fortunately, orbital mechanics would give us some time, perhaps months or years, before this fiery end. The Sun itself would face its own crisis. The delicate balance between gravitational collapse and the outward pressure generated by nuclear fusion would be disrupted. With stronger gravity, the Sun would compress more tightly, increasing the rate of fusion in its core. It would burn brighter and hotter, but exhaust its fuel more quickly. Throughout the galaxy, stars would follow similar paths. Some, particularly those already near the end of their life cycles, might be compressed enough to trigger supernovae, exploding with unimaginable force. Others might collapse directly into neutron stars, or black holes, without the usual stellar phases. The night sky would be alive with these stellar catastrophes, a cosmic fireworks display, signaling the end of an era. On larger scales, galaxies themselves would contract, their stars drawing closer together. The dance of galactic merger would accelerate as gravity pulled neighboring galaxies toward each other with greater force. Over millions of years, the entire universe would become more compacted, its expansion slowed or even reversed by the strengthened gravitational pull. But what about the opposite scenario? What if gravity suddenly weakened, with G dropping to half its current value? On Earth, your weight would instantaneously decrease. You might feel a sudden lightness, perhaps even becoming temporarily airborne, if you happen to be jumping at the exact moment of change. The experience would be similar to what astronauts feel in reduced gravity environments, though not as extreme as full weightlessness. Buildings and structures would suddenly be over-engineered for the new gravitational conditions. They wouldn't collapse, but new constructions could use less material, reaching higher with more slender profiles. Bridge spans could extend further, and architecture would enter a new era of possibilities. The oceans would become less tightly bound to Earth, with sea levels rising at coastlines as water redistributed itself around the globe. The atmosphere too would extend further from Earth's surface, becoming less dense at ground level, but reaching higher into space. Our planet's orbit would begin to widen, moving us incrementally away from the Sun. Earth would gradually cool as it received less solar energy. Without intervention, we would eventually drift into a deep freeze, though again, orbital mechanics would make this a slow process. The Sun would expand slightly as the reduced gravity allowed its outer layers to extend further into space. The pressure at its core would decrease, slowing the rate of nuclear fusion. The Sun would dim and cool, extending its lifespan, but providing less energy to its planetary system. Stars across the cosmos would follow this pattern, expanding and cooling. Many would no longer be able to sustain the temperatures and pressures needed for nuclear fusion, their fires flickering out as they faded into dim stellar remnants. Star formation would become more difficult as gas clouds would struggle to collapse under the weakened gravitational attraction. Galaxies would begin to dissolve, their stars no longer bound tightly enough to maintain their characteristic spiral or elliptical shapes. The majestic structure of the cosmic web, those vast interconnected filaments of galaxies stretching across the universe, would gradually dissipate, its architecture dependent on the exact strength of gravitational attraction. These scenarios assume sudden, uniform changes in the gravitational constant. But physics suggests other possibilities too. What if gravity changed not suddenly but gradually, increasing or decreasing over thousands or millions of years? Life and cosmic structures might have time to adapt to the slowly changing conditions, evolving new forms suited to the altered gravitational regime. Or what if gravity changed not uniformly, but locally, becoming stronger in some regions of space and weaker in others? We might find gravity wells, where the local gravitational constant was significantly higher, creating pockets of intense space-time curvature without the mass normally required for such effects. Conversely, gravity hills might exist where the gravitational force was unusually weak, creating regions where objects seemingly defied normal physical law. Such variations could lead to gravity weather, changeable conditions in the gravitational field that might affect space travel, or even planet-bound lives if the fluctuations were significant enough. Interstellar travelers would need gravitational forecasts alongside radiation warnings and micrometeoroid alerts. Could gravity even reverse itself, becoming repulsive rather than attractive? This seems to violate our fundamental understanding of general relativity, where mass and energy always create positive curvature in space-time. But cosmologists already invoke a repulsive force to explain the accelerating expansion of the universe, the mysterious dark energy that pushes space itself apart. If gravity could somehow flip its sign, becoming negative g rather than positive g, mass would repel rather than attract. Objects would be flung away from Earth, launched into space by the suddenly repulsive ground. Planets would be expelled from their solar systems. Stars would explode as their constituent matter violently repelled itself. Galaxies would shatter, their components dispersed across the growing void. The universe itself would experience hyperinflation far beyond the current accelerating expansion. Space would grow at an exponential rate, quickly carrying gravitationally bound structures beyond their own event horizons, creating countless pocket universes causally disconnected from each other. Cosmic structure would dissolve into an ever-thinning mist of isolated particles. Could such extreme scenarios actually happen? Our current understanding of physics offers little support for the idea of changing gravity, but theoretical frameworks do exist that might accommodate varying fundamental constants, including g. In some theories, gravity's strength might be tied to the value of a scalar field permeating the universe. If this field changed, perhaps through a phase transition similar to water freezing into ice, the gravitational constant could shift along with it. Such changes might be triggered by conditions exceeding certain critical thresholds, much as water only freezes when temperature drops below 0 degrees Celsius. Modified theories of gravity, developed as alternatives to dark matter or dark energy, sometimes predict effective changes in gravitational strength across different scales or in different environments. While not precisely the same as a changing gravitational constant, the observable effects might be similar from our perspective. Certain quantum gravity approaches suggest that what we experience as continuous spacetime might actually have discrete atomic structure at the smallest scales. If true, the gravitational constant might emerge from more fundamental processes, potentially subject to quantum fluctuations or evolutionary changes over cosmic timescales. Even without a complete change in the gravitational constant, variations in gravitational wave propagation could alter how gravity affects distant objects. If gravitational waves, those ripples in spacetime confirmed by LIGO in 2016, change their properties, gravity's action across cosmic distances might strengthen or weaken accordingly. The cosmos has already shown us one form of altered gravity. Dark energy, whatever its true nature, effectively acts as anti-gravity on the largest scales, accelerating the expansion of space itself. This cosmological constant, denoted by the Greek letter lambda in Einstein's equations, suggests the relationship between space, time, and gravity is more complex than we once believed. Perhaps the most profound implications of changing gravity would be philosophical rather than physical. A shifting gravitational constant would undermine the concept of immutable natural law. If one constant can change, why not others? The boundary between physical law and historical accident would blur, suggesting a universe more mutable, more contingent than science has traditionally assumed. Our cosmic history would no longer be deterministic, a straight line from Big Bang to heat death governed by fixed physical law. Instead, it would be punctuated by transitions between different gravitational regimes, each with its own characteristic structures and evolutionary pathways. The universe would have epochs not just of matter and energy distribution, but of fundamental law itself. Such a universe requires a different kind of mathematics to describe it, not just unchanging equations, but systems that can model phase transitions in the underlying rules themselves. It would demand a metaphysics, a framework for understanding how physical law itself might emerge, evolve, and transform. For conscious beings like ourselves, evolved in and adapted to a specific gravitational context, changes in G would be more than physically catastrophic. They would challenge our very conceptual framework for understanding reality. Our neural architecture, our embedded knowledge of how objects move and fall, our intuitive physics, all are calibrated to the current gravitational regime. Yet even in such extreme circumstances, the human capacity for adaptation might find ways to survive and even thrive. Given sufficient warning and technological capability, we might construct habitats shielded from the worst effects of gravitational change, generation ships designed to weather the storm of changing physical law. Perhaps advanced civilizations might even learn to manipulate the gravitational constant locally, creating bubbles of altered G for specific engineering or research purposes. Gravity engineering could become the ultimate technology, allowing the adjustment of physical law itself rather than merely working within its constraints. For now, these remain speculations at the edge of known physics. But by contemplating what would happen if gravity changed, we gain insight into how deeply this force shapes our universe and ourselves. We see more clearly the remarkable harmony of current physical laws that allows complexity and consciousness to exist. And we open our minds to the profound possibility that the cosmos might be even stranger, more malleable, and more wondrous than we have dared to imagine. If gravity shapes the large-scale architecture of our universe, electromagnetism gives it color, chemistry, and complexity. This fundamental force governs how atoms form bonds, how light interacts with matter, how electricity flows through conductors. It's responsible for nearly all the phenomena we experience in daily life, from the friction that keeps your feet from slipping on the floor, to the light entering your eyes that allows you to see the world. Electromagnetism operates at a strength approximately 10 to the 36 power times greater than gravity. While gravity's influence accumulates with mass, creating its dominance at cosmic scales, electromagnetic forces rule the atomic and molecular realms. They bind electrons to nuclei in precise configurations, determining the chemical properties of every element and compound. What might happen if this force suddenly changed its character? If the electromagnetic constant, typically represented by the Greek letter alpha, the fine structure constant, shifted from its current value of approximately 1 divided by 137. Let's first consider a strengthening of the electromagnetic force. If alpha increased significantly, perhaps doubling in value, the effects would begin at the subatomic level, but quickly cascade upward to transform everything we know. Electrons would be bound more tightly to atomic nuclei, orbiting closer to the central protons. Atomic radii would decrease across the periodic table. This compression would fundamentally alter how atoms interact with one another, reshaping the very foundations of chemistry. Chemical bonds would become stronger, but also less flexible. Molecules would hold together more firmly, requiring more energy to break apart. Reaction rates would change dramatically, with some reactions accelerating while others became nearly impossible. The delicate balance of chemical processes that sustains living organisms would be profoundly disrupted. Water, that extraordinary molecule so essential to life as we know it, would behave differently. Its polarity would increase, strengthening hydrogen bonds and raising its boiling point significantly. Oceans might not evaporate easily enough to form clouds. The water cycle that distributes this precious resource across our planet could falter. Light itself would change. With stronger electromagnetic interactions, photons would interact more frequently with charged particles. The transparency of air, water, and biological tissues would decrease. Sunlight might not penetrate as deeply into ocean waters, affecting marine ecosystems dependent on photosynthesis. In living organisms, the precisely calibrated electromagnetic interactions that allow proteins to fold into functional shapes would be altered. DNA bases would pair with different strengths, potentially destabilizing the genetic code. Cell membranes, maintained by careful balances of electromagnetic forces, might become too rigid or too permeable. Your own sensory experience would transform. Colors would shift as the energies of electron transitions in atoms changed, altering the wavelengths of absorbed and emitted light. The sky might no longer appear blue. Plants might no longer appear green. The palette of the world would be repainted with unfamiliar hues. The electrical activity in your nervous system would be affected too. Signals might propagate differently along neural pathways. The carefully balanced electrochemistry of thought itself could be disrupted, altering consciousness in ways impossible to predict from our current perspective. If the electromagnetic force weakened instead, a different set of transformations would unfold. Electrons would orbit farther from their nuclei, making atoms larger and more loosely bound. Chemical bonds would weaken, making molecules less stable and more reactive. Many solid materials might simply fall apart as their atomic bonds failed to maintain structural integrity. Others might remain intact but become softer, more pliable, or more volatile. Materials we depend on for construction, transportation, and technology could become unusable overnight. Some chemical reactions vital to life might cease altogether if the activation energy could no longer be overcome at biological temperatures. Others might accelerate wildly, consuming resources at unsustainable rates. The balanced networks of reactions that comprise metabolism would unravel, making life as we know it impossible. The optical properties of matter would change in this scenario too. With weaker interactions between photons and charged particles, light would travel more freely through various media. The atmosphere might become more transparent to harmful radiation from space. The protective ozone layer could lose its effectiveness, exposing Earth's surface to damaging ultraviolet light. On a more fundamental level, a significant change in the electromagnetic constant would alter the relationship between electricity and magnetism themselves. The speed of light, which emerges from the electromagnetic properties of vacuum, might change. This would have profound implications for the structure of space-time itself, potentially requiring revisions to special relativity. Modern technology, almost entirely dependent on precisely tuned electromagnetic phenomena, would fare poorly in either scenario. Electronic devices rely on semiconductor materials whose properties would be fundamentally altered by changes in alpha. Electrical conductors might become insulators or vice versa. Communication systems, power distribution networks, and computing infrastructure could all fail in complex and catastrophic ways. These scenarios assume large changes in the electromagnetic constant, perhaps doubling or halving its value. But even tiny variations would have significant effects over time. If alpha changed by just 1%, chemistry would be noticeably different. Many chemical compounds that are stable in our world might become unstable, while new possibilities for molecular structures would emerge. Stellar processes would be affected too. The delicate balance of forces in stellar interiors, where electromagnetic repulsion between protons competes with the strong nuclear force and gravity, would shift. Stars might burn their nuclear fuel at different rates, altering their lifespans and the elements they produce through nucleosynthesis. The habitable zones around stars, those regions where planets can maintain liquid water on their surfaces, would shift position. Planets that currently support life might become too hot or too cold. The emergence and evolution of life throughout the cosmos would follow different pathways under altered electromagnetic regimes. Could such changes actually occur? As with gravity, our standard models of physics treat the electromagnetic constant as truly constant, unchanging across space and time. But various theoretical frameworks suggest mechanisms by which alpha might vary. In certain unified field theories, the fine structure constant emerges from more fundamental parameters that could potentially evolve with cosmic time. Some versions of string theory allow for variations in alpha across different regions of a multiverse, with our observable universe representing just one domain with its particular electromagnetic value. The mechanisms for such variation might involve scalar fields similar to those proposed for changing gravity. These fields could couple to electromagnetic phenomena, effectively altering the strength of these interactions as the field values shifted. The changes could be triggered by phase transitions in the early universe, or by threshold effects as cosmic parameters cross critical values. Such variations need not be uniform. We might imagine a universe where alpha took different values in different regions of space, creating a mosaic of electromagnetic regimes. The boundaries between these regions would be exotic transition zones, where the laws of chemistry themselves changed gradually from one form to another. If electromagnetism could change suddenly, the effects would be even more dramatic than those of shifting gravity. While gravitational changes would initially impact large-scale structures, electromagnetic variations would immediately disrupt the atomic and molecular foundations of matter itself. There would be no time for adaptation, no gradual evolution of new forms suited to the altered conditions. Yet the interplay between these forces creates additional complexities. If both gravity and electromagnetism change simultaneously, the effects would not simply add together, but would interact in complex and potentially unpredictable ways. Strengthened gravity combined with weakened electromagnetism might allow for novel forms of matter with no analog in our current universe. This complexity points to a deeper truth about physical law. The constants of nature do not exist in isolation, but form an interconnected web. Changes in one parameter reverberate through the entire system, sometimes with counterintuitive results that defy simple extrapolation. The apparent fine-tuning of these constants for complexity and life becomes even more remarkable when we consider these interconnections. The possibility space of physical law appears to contain vast regions where complexity cannot emerge, with only rare combinations of parameters allowing for the rich structures we observe. Perhaps the most profound implication of changing electromagnetic forces would be the disruption of light itself. Light is more than just illumination. It's a fundamental information carrier linking distant parts of the cosmos. If the properties of photons changed, the very dialogue between matter and energy that constitutes our universe would be rewritten. The universe would not go dark in the conventional sense, but the language of light would change. Stars would still radiate energy, but the spectrum of that radiation would shift. Matter would still absorb and emit photons, but at different wavelengths and with different probabilities. The cosmic conversation written in spectral lines and absorption patterns would be translated into an unfamiliar dialect. For conscious observers like ourselves, this transformation would be particularly disorienting. Our sensory systems have evolved to detect and interpret the particular electromagnetic regime of our universe. Our eyes are exquisitely tuned to the visible spectrum, that narrow band of wavelengths where our sun radiates most strongly and where the atmosphere is coincidentally transparent. In a universe with altered electromagnetism, this harmony between radiation, transparency, and perception would be disrupted. New windows onto the cosmos might open as different wavelengths became more detectable, while familiar channels of information closed. Consciousness itself might need to develop new frameworks for organizing and interpreting sensory data from this changed electromagnetic environment. The effects would extend beyond perception to cognition itself. The electrochemical processes of neural transmission rely on specific electromagnetic properties of cell membranes, neurotransmitters, and ion channels. Changes in these properties would alter how information travels through neural networks, potentially changing the speed, reliability, and pattern of thought processes. Yet consciousness has proven remarkably adaptable throughout evolutionary history. If changes in electromagnetism occurred gradually enough, and if they left some window of complexity open, perhaps minds could evolve that were suited to the new regime. These minds might organize their experience in ways we cannot currently imagine, perceiving and conceptualizing a universe that operated according to different electromagnetic rules. We might ask whether such altered forms of consciousness would recognize the change at all. Without access to the previous electromagnetic regime for comparison, would they simply take their universe as given, building sciences and philosophies based on the altered constants they measured? Physical law might have a history, but observers embedded within a particular phase might perceive it as eternal and unchanging. This thought experiment reveals something profound about our own relationship to physical law. We have no memory of previous cosmic regimes, if any existed. We measure constants as they are today and project that measurement backward and forward in time, assuming constancy because we have known nothing else. Our confidence in unchanging physical law might in part reflect our limited temporal perspective. The search for variations in alpha and other constants thus takes on additional significance. It is not merely a test of specific theories, but a probe into the very nature of physical law itself. Are the patterns we call laws truly timeless? Or might they have evolutionary histories of their own? Is the cosmos governed by eternal mathematical truth? Or is it a historical entity whose very rules have unfolded and developed over time? For now, electromagnetism continues to behave consistently across all our measurements. The fine structure constant appears truly constant to the limits of our observational precision. The chemistry that enables our bodies, our technologies, and our planet's ecosystems continues to operate according to familiar principles. But the question persists, urging us toward ever more precise measurements and ever more comprehensive theories. In the dance between theoretical possibility and empirical constraint, our understanding of the fundamental forces continues to evolve, revealing new layers of complexity in the cosmic tapestry that surrounds and constitutes us. If electromagnetism were to change, our universe would become unrecognizable. Yet in contemplating this possibility, we gain a deeper appreciation for the remarkable harmony of forces that allows our current reality to exist. We see more clearly how the constants of nature, whatever their ultimate origin, have conspired to create a cosmos capable of observing and understanding itself through conscious minds like our own. Diving deeper into the fabric of reality, we arrive at the realm of particle physics, where matter and energy reveal their most fundamental nature. Here, the Standard Model reigns, a theoretical framework that describes the elementary particles and 3 of the 4 fundamental forces that govern their interactions. The Standard Model is one of humanity's greatest intellectual achievements, the culmination of decades of experimental discovery and theoretical insight. It classifies all known elementary particles, 6 types of quarks, 6 types of leptons, 4 gauge bosons that carry forces, and the Higgs boson that gives particles their mass. This model isn't just descriptive, it's predictive. It allows physicists to calculate with astonishing precision how particles will behave in various circumstances. The magnetic moment of the electron, for instance, can be predicted by the Standard Model to an accuracy of better than 1 part in a trillion, equivalent to measuring the distance between New York and Los Angeles with an error smaller than the width of a human hair. But the Standard Model isn't just a collection of particles. It's a carefully balanced mathematical structure where masses, charges, and coupling constants determine how these particles interact. Each parameter is precisely tuned, measured through countless experiments at particle accelerators and cosmic observatories around the world. What would happen if these parameters changed? If the masses of fundamental particles shifted, or if the strengths of their interactions altered? The consequences would be at least as profound as those of changing gravity or electromagnetism, perhaps even more so, as they would rewrite reality at its most fundamental level. Let's consider the mass of the electron, one of the simplest parameters we might imagine changing. In our universe, the electron has a mass of approximately 9.1 times 10 to the negative 31 kilograms, about 1/1836 the mass of a proton. If the electron mass increased significantly, atoms would shrink. Electrons would orbit closer to nuclei, just as we saw with strengthened electromagnetism. But the effect would be different in important ways. Chemical properties would change dramatically, but not uniformly across the periodic table. Elements would retain their electromagnetic behavior, while their physical characteristics transformed. Heavier electrons would make many nuclear decay processes more energetically favorable. Some currently stable isotopes might become radioactive. Others might transition from one decay mode to another. The delicate balance of nuclear reactions in stellar cores would shift, potentially altering stellar evolution and nucleosynthesis, the forging of heavy elements in stellar furnaces. Conversely, if electrons became lighter, atoms would grow larger. Chemical bonds would lengthen and weaken. Molecules would become more fragile, potentially breaking apart under thermal vibrations that they currently withstand. Matter as we know it might literally fall apart if electron mass decreased beyond a certain threshold. The ratio between electron and proton masses is particularly important. This ratio affects everything from the stability of molecular hydrogen, the simplest molecule and one crucial for star formation, to the vibrational frequencies of more complex molecules that enable biochemistry. Even more dramatic would be changes to quark masses. Quarks are the constituents of protons and neutrons, bound together by the strong nuclear force. In our universe, the up quark has a mass of about 2.2 megaelectron volts, while the down quark is around 4.7 megaelectron volts. If these masses change significantly, the properties of protons and neutrons would be fundamentally altered. The neutron is currently slightly heavier than the proton by about 0.1%, making free neutrons unstable. They decay into protons, electrons, and antineutrinos with a half-life of about 10 minutes. If quark masses shifted enough to make protons heavier than neutrons, the situation would reverse. Protons would become unstable, decaying into neutrons, positrons, and neutrinos. Hydrogen, whose nucleus consists of a single proton, could no longer exist as a stable element. Without hydrogen, water cannot form. Without water, life as we know it becomes impossible. The stability of atomic nuclei depends on a complex interplay between the electromagnetic repulsion of positively charged protons and the attractive strong nuclear force. Change the masses of quarks, and you change the effective range and strength of these nuclear forces, potentially destabilizing elements that are currently stable or stabilizing ones that are currently radioactive. The periodic table itself might be rewritten, with different elements occupying the role of stable, abundant building blocks of matter. Chemistry would follow entirely different rules, with novel bonding patterns and molecular structures possible. What we understand as matter would be reinvented from the subatomic level upward. Beyond mass, changes to other particle properties would have equally profound effects. Consider the electric charge of the electron. In our universe, the electron carries exactly the same magnitude of charge as the proton, just with opposite sign. This precise balance ensures that atoms are electrically neutral, allowing matter to clump together under gravity without being torn apart by electromagnetic repulsion. If the electron's charge differed even slightly from the protons, atoms would carry a net electric charge. Matter would strongly repel other matter. Planets, stars, and even living organisms could not form. The large-scale structure of the universe would be completely different, dominated by electromagnetic forces rather than gravity at every scale. Coupling constants determine the strength of interactions between particles and force-carrying bosons. The strong coupling constant, for instance, governs how quarks interact via the strong nuclear force. If this constant increased significantly, quarks would be bound more tightly within protons and neutrons. These particles might become smaller and more rigid, altering their behavior in nuclear reactions. A stronger strong force might also change the balance between nuclear fusion and fission. Fusion might become easier to initiate and sustain, potentially allowing for different stellar processes, or even making fusion more accessible as an energy source on Earth. Nuclear weapons would become even more destructive, releasing greater energy from the same amount of material. If the strong force weakened instead, quarks might not be confined within hadrons at all. In extreme cases, they could be liberated as free particles, creating a form of matter called quark matter, or a quark-gluon plasma. Under normal conditions, this exotic state of matter only existed in the first microseconds after the Big Bang, and perhaps in the cores of neutron stars, or in high-energy particle collisions. A weakened strong force could make it the dominant form of matter in the universe. The weak nuclear force, responsible for certain types of radioactive decay, also plays a crucial role in stellar nucleosynthesis. The conversion of hydrogen to helium in the Sun's core relies on weak interactions to transform protons into neutrons. If the weak coupling constant changed, stellar fusion would proceed at different rates, potentially making stars burn brighter and shorter-lived, or dimmer but more enduring. Neutrinos, nearly massless particles that interact only via the weak force and gravity, permeate the universe in vast numbers. They pass through ordinary matter almost without interaction in our current physical regime. If the weak force strengthens significantly, neutrinos might begin to interact more strongly with ordinary matter, transferring energy and momentum in noticeable ways. Conversely, if the weak force diminished, processes like beta decay would slow or cease altogether. Many radioactive elements would become stable. The nuclear reactions in stellar cores would falter, potentially preventing the synthesis of elements heavier than helium. A universe with a significantly weaker weak force might contain only the lightest elements, lacking the chemical complexity necessary for life as we know it. The Higgs field, discovered in its boson form at the Large Hadron Collider in 2012, gives elementary particles their mass through their interactions with it. Different particles couple to the Higgs field with different strengths, resulting in their observed masses. A change in the Higgs field's vacuum expectation value would rescale all particle masses simultaneously, maintaining their ratios but altering their absolute values. If the Higgs field strengthened, All massive particles would become heavier. Chemical bonds would change as electron masses increased. Nuclear processes would transform as quarks gained mass. The universe would essentially become more massive, with all the consequences that entails. If the Higgs field weakened, particles would become lighter. In the extreme case where the Higgs field vanished entirely, most fundamental particles would become massless, traveling at the speed of light like photons. Matter as we know, it could not exist. No atoms, no chemistry, no solid objects, just a universe of radiation and massless particles streaming through space-time at light speed. The most dramatic scenario might involve changes to multiple particle properties simultaneously, especially if these changes weren't coordinated to maintain the delicate balances that allow for stable matter. For instance, if the ratio between the electromagnetic and strong forces changed significantly, atomic nuclei might become unstable against electromagnetic repulsion. All elements heavier than hydrogen could spontaneously undergo nuclear fission, effectively ending chemistry and biology in a cascade of nuclear destruction. Could such changes actually occur? The Standard Model treats its approximately 26 free parameters as constants, but more fundamental theories might reveal them as emergent properties that could vary in different conditions. String theory, for instance, suggests that particle properties emerge from the geometry of tiny, curled-up extra dimensions, which might theoretically reconfigure through cosmic phase transitions. Various grand unified theories propose that the fundamental forces, which appear distinct at our everyday energy scales, merge into a single unified force at extremely high energies, similar to those present in the earliest moments after the Big Bang. If true, changes in the unification energy or coupling constant could cascade down to alter all the separate forces we observe today. Some theories suggest that what we perceive as elementary particles might actually be excitations of more fundamental fields, similar to how phonons emerge as quasi-particles in solid-state physics. Changes in the properties of these underlying fields could alter the entire spectrum of particles and their interactions. The discovery of the Higgs boson confirmed that seemingly empty space is actually filled with the Higgs field. This revelation supports the broader concept of a cosmos permeated by multiple fields, whose values might potentially shift through cosmic evolution or in different regions of space. Vacuum decay theories, which we'll explore more deeply in a later chapter, suggest that our current vacuum state might be metastable, potentially tunneling to a lower energy state where fundamental parameters take different values. This would effectively rewrite the Standard Model across the affected region, creating an expanding bubble of altered physics that could eventually encompass the observable universe. For conscious observers like ourselves, changes to the Standard Model parameters would be even more fundamental than alterations to gravity or electromagnetism. While those forces shape how existing particles interact, the Standard Model parameters determine which particles can exist at all and what properties they possess. Our very bodies consist of arrangements of Standard Model particles. Our biochemistry depends on their specific properties. Our consciousness emerges from neural processes governed by these particle interactions. Changes to the fundamental parameters would disrupt not just our environment, but our physical constitution at its most basic level. Yet even in this extreme scenario, the concept of adaptation returns in a speculative form. If physical parameters can vary across space or time, regions might exist where different forms of complexity could emerge based on the specific values present there. What we consider fine-tuned constants necessary for life might simply be the particular set that allows our form of complexity to arise. Alternative biochemistries based on different stable elements, different bonding patterns, or even different fundamental forces might be conceivable in regimes with altered Standard Model parameters. Consciousness might emerge from substrates utterly unlike our carbon-based neural networks, perhaps based on patterns in plasma, exotic quantum states, or forms of matter we cannot currently imagine. This speculation extends to what physicists call the landscape of possible physical theories. If something like string theory proves correct, with its vast multitude of possible vacuum states corresponding to different physical laws, our universe might be just one realization among countless possibilities. Other regions of the multiverse might host different physical constants, different particles, different forces, and potentially different forms of complexity and consciousness. For now, these remain theoretical possibilities. The Standard Model continues to match all experimental observations with remarkable precision. No variations in particle properties have been conclusively detected across space or time, despite increasingly sensitive experiments designed to find them. But the questions persist, driving research at the frontiers of particle physics. New accelerators probe ever higher energies, seeking hints of physics beyond the Standard Model. Cosmological observations search for signs of primordial phase transitions, where fundamental parameters might have shifted. Theoretical physicists develop frameworks that might explain why particles have the exact properties we measure. In contemplating changes to the Standard Model, we confront the deepest questions about the nature of physical law and the origins of complexity. We recognize how remarkably balanced our current physical regime is, how precisely calibrated to allow for the emergence of structure, chemistry, and ultimately, minds capable of comprehending the very laws that made them possible. How stable is our universe? This seemingly abstract question has profound implications for everything we know. We tend to assume that the cosmos, while dynamic in its contents, remains fundamentally constant in its rules. Stars are born and die. Galaxies collide and merge. But the underlying physical laws continue unchanged, eternal guidelines governing an ever-evolving reality. But what if this assumption is wrong? What if the universe itself exists in a precarious state, capable of transitioning to an entirely different physical regime? This unsettling possibility emerges from some of our most advanced theoretical frameworks and raises profound questions about the past, present, and future of cosmic reality. To understand the concept of universal stability, we must first venture into the strange realm of quantum field theory. According to this framework, seemingly empty space is not empty at all, but filled with fields that permeate the entire cosmos. Every type of elementary particle has its corresponding field, the electron field, the Higgs field, various quark fields, and so on. These fields can exist in different energy states, much as water can exist as ice, liquid, or vapor, depending on temperature and pressure. The particular configuration of these fields, collectively called the vacuum state, determines the properties of empty space, and by extension, the laws of physics that operate within it. Our current understanding suggests that the vacuum state of our universe might not be in its lowest possible energy configuration. Instead, it may exist in what physicists call a metastable state, like a ball resting not at the bottom of a valley, but in a small depression partway up a hillside. The ball appears stable in its current position, but with enough of a push, it could roll down into a deeper valley, settling into a more stable configuration. This concept, known as false vacuum decay, suggests that our universe could potentially transition to a different vacuum state, one with lower energy and, crucially, different physical laws. Such a transition wouldn't just change the contents of the universe, it would rewrite its fundamental operating system. How might such a transition occur? Quantum mechanics provides a mechanism through the phenomenon of quantum tunneling. Even when classical physics would prevent a system from changing states because of an energy barrier, quantum mechanics allows for the possibility of tunneling through that barrier with some probability. In the context of vacuum decay, quantum fluctuations could potentially nucleate a bubble of true vacuum, a small region where the fields have tunneled to their lower energy state. This bubble would have different physical laws inside it than the surrounding false vacuum of our current universe. The boundary of this bubble would expand outward at nearly the speed of light. From the perspective of observers like ourselves in the false vacuum, this expansion would appear as an advancing wall of changed physics, a spreading zone where the familiar laws of nature no longer apply. The interior of this bubble would represent an entirely new universe, with different fundamental constants, different particles, and different interactions. The specific nature of this new reality would depend on the precise configuration of fields in the true vacuum state. Would we see this transition coming? Almost certainly not. Since the boundary of a vacuum decay bubble expands at nearly light speed, no warning could reach us before the boundary itself arrived. There would be no astronomical observations, no measurable changes in physical constants, no advance notice of any kind. One moment, physics as usual. The next moment, the rules completely rewritten. What would happen to matter, energy, and living things as this boundary passed? The most likely outcome is total destruction. Atoms configured according to one set of physical laws cannot remain stable when those laws suddenly change. Matter would instantly decompose and reconfigure according to the new physical regime, if stable matter was even possible in the new vacuum state. For conscious observers like ourselves, the experience would be instantaneous obliteration, with no possibility of adaptation or survival. The transition would happen faster than neural signals could travel, faster than a single thought could form. One moment existence, the next moment transformation so fundamental that nothing recognizable would remain. This scenario sounds like science fiction, but it emerges from serious theoretical physics. The calculation of our vacuum stability depends on precise measurements of particle properties, particularly the mass of the Higgs boson and the top quark. Current measurements place us in an interesting position, neither clearly stable nor definitively unstable, but somewhere in the metastable region where decay is possible but not certain. The lifetime of a metastable vacuum can be extraordinarily long. Calculations suggest that if our vacuum is indeed metastable, the expected time before a decay event is likely far longer than the current age of the universe, perhaps 10 to the power of 100 years or more. On human or even cosmic timescales, the risk of imminent vacuum decay appears negligible. But probability becomes a strange concept when applied to the only universe we know. A small probability multiplied by infinite time approaches certainty. If our vacuum is truly metastable, then vacuum decay becomes not a question of if, but when. And in an infinite or extremely long-lived universe, even exceedingly improbable events eventually occur. This raises an interesting anthropic consideration. If vacuum decay is possible but hasn't happened yet, we might be observing our universe during a cosmologically brief window of metastability, a fleeting period when complexity and consciousness can exist before an inevitable transition to a different physical regime. Vacuum decay represents one potential mechanism for changing physical laws, but other theoretical frameworks suggest additional possibilities. Some versions of string theory, for instance, propose that what we experience as physical constants might actually be fields that can dynamically evolve over time or vary across space. These fields, sometimes called moduli, could potentially shift from one value to another through various mechanisms. Cosmic phase transitions, similar to how water freezes into ice when temperature drops below a critical value, might cause fundamental fields to reconfigure, altering the effective physical laws. The early universe likely experienced such phase transitions. According to the standard cosmological model, fundamental forces that appear distinct today, such as electromagnetism and the weak nuclear force, were unified at the extreme temperatures present shortly after the Big Bang. As the universe expanded and cooled, symmetry-breaking transitions separated these forces, establishing the physics we currently observe. Could similar transitions occur in the future? Theoretical models suggest various possibilities. The dark energy that drives the accelerating expansion of our universe might evolve over time, potentially triggering changes in other physical parameters. The hypothetical fields that determine coupling constants or particle masses might shift to new equilibrium values as cosmic conditions change. Unlike vacuum decay, some of these transitions might occur gradually rather than instantaneously. creating a slow drift in physical laws rather than a sudden rewriting. Such gradual changes might be detectable through precision measurements of fundamental constants over time, or through careful observations of light from distant cosmic sources, allowing us to compare physics in the distant past with current conditions. Beyond these theoretical mechanisms for changing physical laws, some cosmological models propose an even more dramatic possibility: multiple universes or regions with different fundamental parameters. The string theory landscape, with its vast number of possible vacuum states, suggests our observable universe might be just one bubble in a much larger multiverse. In chaotic inflation models, our universe could be one of countless expanding regions, each with potentially different physical laws determined by how fields settled into their vacuum states during the inflationary epoch. These different regions would be causally disconnected from each other, effectively separate universes with their own distinct physics. If these models reflect reality, then physical laws might be contingent rather than necessary, accidents of cosmic history rather than inevitable mathematical truths. Our particular set of laws would represent just one possibility among many, selected not because they're uniquely possible, but because they allow for observers like us to evolve and ask these questions. This perspective transforms our understanding of fine-tuning. Rather than seeing our universe's life-friendly parameters as evidence of purpose or incredible cosmic coincidence, we might understand them as an observational selection effect. In a vast multiverse with regions of different physics, conscious observers necessarily find themselves in the rare regions where physics allows consciousness to emerge. These speculations extend beyond current observational evidence, but they raise profound questions about the nature of physical law itself. Are the patterns we call laws truly fundamental and immutable, or are they emergent and potentially changeable? Is mathematics discovered or invented? And does it constrain what physical laws can exist? Even without definitive answers to these questions, the possibility of changing physical laws challenges us to reconsider our relationship with the cosmos. We typically imagine ourselves as temporary inhabitants of an eternal stage, players that come and go while the theatre remains unchanged. But if physical laws themselves can evolve or transition, then the stage itself is temporary, the setting as transient as the actors. This perspective might seem unsettling, removing what appeared to be the one fixed reference point in an otherwise changing universe, but it also connects us more deeply to cosmic processes. Rather than existing as anomalies in an otherwise immutable reality, we might be participants in a universe that evolves at all levels, from the distribution of matter and energy to the fundamental rules themselves. The question of universal stability also has practical implications for the far future of intelligence. Civilizations hoping to survive for billions or trillions of years must contend not just with the challenges of entropy and cosmic evolution under current physical laws, but with the possibility that those laws themselves might change unpredictably. True vacuum decay presents a particularly troubling scenario, since it would propagate at light speed with no warning, offering no possibility of escape or adaptation. But even gradual changes in physical constants could potentially disrupt the delicate balance that allows for atoms, chemistry, and biological or technological complexity. Some speculative thinkers have pondered whether sufficiently advanced civilizations might somehow engineer the stability of their region of space-time, perhaps finding ways to prevent vacuum decay or to influence how fundamental parameters evolve. Such capabilities remain far beyond our current science and technology, but they highlight how the question of cosmic stability could eventually transform from philosophical speculation to practical concern. For now, our universe appears remarkably stable. Measurements of fundamental constants across space and back through billions of years of cosmic history show consistency to high precision. No signs of an advancing vacuum decay bubble have been detected, though such detection would be possible only after the boundary had already passed, rendering the observation moot. The Higgs boson's measured mass places our vacuum in the metastable region according to current calculations, but uncertainties remain. New physics beyond the standard model, yet to be discovered, could potentially affect these calculations, either reinforcing our vacuum's metastability or suggesting greater stability than currently estimated. In the face of these uncertainties, we continue our cosmic journey, studying the laws of physics while acknowledging that they might have histories and futures beyond our current understanding. We measure constants with increasing precision, not just to refine our current models, but to search for the subtle variations that might reveal deeper patterns of cosmic evolution. And in moments of philosophical reflection, we contemplate the remarkable coincidence or inevitable consequence that we exist during a period when physical laws allow for complexity, chemistry, biology, and consciousness. Whether by purpose, chance, or anthropic selection, we find ourselves in a universe currently stable enough and configured appropriately for observers to contemplate their own existence and the laws that make it possible. This precarious position, balance between cosmic history and an uncertain future, invites both humility and wonder. We are not merely observers of an eternal cosmic play, but participants in an evolving reality whose fundamental nature continues to surprise and challenge our deepest assumptions. The universe's stability remains an open question, one that connects the most abstract theoretical physics with the most profound philosophical inquiries about existence, time, and the nature of physical law. In exploring this question, we may ultimately learn as much about ourselves, the curious conscious entities asking these questions, as about the cosmos that produced us. Having explored how changes in physical laws might affect fundamental particles, forces, and the stability of our universe, we now turn our gaze outward to the grandest scales. How would shifting physical constants reshape the cosmos itself? What would happen to galaxies, cosmic structure, and the very fate of the universe if the fundamental rules suddenly changed? The cosmos we observe appears exquisitely structured. Hundreds of billions of galaxies arrange themselves in an intricate cosmic web, with vast filaments of matter surrounding equally vast voids. This large-scale architecture emerges from the interplay between gravity, which pulls matter together, and the cosmic expansion, which drives space itself to stretch. The balance between these competing influences depends critically on the values of fundamental constants. Consider the cosmological constant, represented by the Greek letter lambda in Einstein's equations, which characterizes the energy density of empty space. In our universe, this constant appears to have a small positive value, driving the accelerating expansion we observe today. But what if it changed? If lambda increased significantly, the cosmic expansion would accelerate dramatically. Galaxies would be pulled away from each other at ever-increasing speeds. Eventually, even individual galaxies would begin to tear apart as the expansive force overcame gravitational binding. Stars would be flung from their galactic homes, planets torn from their stars, and ultimately, atoms themselves might be ripped apart in what physicists call the Big Rip. This cosmic doomsday scenario would effectively end all structure in the universe. No galaxies, no stars, no planets, no possibility for the complex chemistry that enables life. The cosmos would become an ever-thinning soup of elementary particles, rushing away from each other into an increasingly vast and empty void. Conversely, if lambda decreased or became negative, cosmic expansion would slow and eventually reverse. The universe would begin to contract, galaxies drawing closer together in a cosmic dance, leading to what scientists call the Big Crunch. As space compressed, temperatures would rise. Galaxies would merge, and stars would collide with increasing frequency as the available volume decreased. In the final stages of this contraction, temperatures would approach and exceed those of the early universe. Matter would decompose into a superhot plasma of elementary particles before potentially reaching a singularity similar to the Big Bang, but in reverse, a point of infinite density where our current understanding of physics breaks down entirely. Some theoretical models suggest that such a big crunch might potentially lead to a bounce and a new period of expansion, a Big Bang emerging from the collapsed previous universe. If physical constants could change during this extreme transition, the new expanding universe might operate according to different physical laws than our own. The gravitational constant G also plays a crucial role in cosmic structure. If G strengthened, the formation of structure would accelerate. Gravity would pull matter together more efficiently, potentially leading to a universe dominated by black holes rather than stars. Galaxies would be more compact, with stars packed closer together, leading to more frequent stellar encounters and gravitational disruptions of planetary systems. A stronger gravitational constant might also affect cosmic expansion, potentially slowing or reversing it depending on the magnitude of the change. The universe might recollapse more quickly than currently predicted, or its expansion might merely slow without ever reversing. If G weakened instead, structure formation would be impeded. Galaxies might become more diffuse or fail to form altogether. Stars would need to be more massive to ignite nuclear fusion against the reduced gravitational compression. Smaller stars like our Sun might never reach the temperatures needed for hydrogen fusion, remaining as failed stars or brown dwarfs. With fewer stars burning, the production of heavy elements through stellar nuclear synthesis would be reduced. The cosmos would remain dominated by hydrogen and helium, lacking the chemical complexity needed for rocky planets and biological systems. Intelligence as we know it might never emerge in such a chemically impoverished universe. Beyond these individual constants, the interplay between different forces shapes cosmic evolution in complex ways. The balance between the initially tiny quantum fluctuations in the early universe and the smoothing effect of cosmic expansion determined the seeds of all current structure, changed the fundamental constants governing quantum mechanics. And this balance shifts, potentially leading to a universe with dramatically different clustering properties. The cosmic microwave background, that faint afterglow of the Big Bang, now cooled to just 2.7 Kelvin, preserves an image of the early universe when it was just 380,000 years old. Its nearly perfect uniformity, with temperature variations of only about 1 part in 100,000, reflects the delicate balance of forces in the early cosmos. If fundamental constants changed, this radiation field would show different patterns. The characteristic scale of fluctuations, which depends on the interplay between gravity, radiation pressure, and the speed of sound in the primordial plasma, would shift. The relative heights of peaks in the power spectrum, which encode information about the composition of the early universe, would change. Such alterations would not merely be of academic interest. These early fluctuations served as the seeds for all subsequent structure formation. Different patterns in the cosmic microwave background would lead to different patterns of galaxies, clusters, and voids, reshaping the entire visible universe. The process of structure formation itself depends critically on the properties of dark matter, that mysterious substance that interacts primarily through gravity and makes up about 85% of all matter in the universe. If the properties of dark matter particles changed, perhaps due to alterations in the physical constants that determine their mass or interactions, the entire history of cosmic structure would be rewritten. Heavier dark matter particles would move more slowly in the early universe, allowing smaller structures to form first, which then merge hierarchically into larger ones. Lighter particles would stream out of small density fluctuations, suppressing the formation of smaller structures and favoring larger ones from the beginning. The galaxies we see, including our own Milky Way, might never have taken shape if dark matter properties were significantly different. The formation of stars, those cosmic furnaces that forge heavy elements and potentially nurture life-bearing planets, depends on a complex interplay of forces and constants. Nuclear fusion in stellar cores relies on the delicate balance between electromagnetic repulsion between positively charged nuclei and the attractive, strong nuclear force that can overcome this repulsion at sufficiently high temperatures and densities. If this balance shifted through changes in the fundamental constants, stellar evolution would follow different pathways. Stars might burn hotter and faster, exhausting their nuclear fuel in cosmic moments rather than billions of years. Or they might fail to ignite altogether, leaving the universe dark and cold, populated by enormous balls of unignited gas. The specific nuclear reactions that dominate stellar burning also depend sensitively on the exact values of physical constants. The triple alpha process, which produces carbon through the fusion of 3 helium nuclei, works only because of a precise resonance in the carbon-12 nucleus discovered by Fred Hoyle. This resonance depends on the fine structure constant and the strong force strength. If these constants changed, the resonance might disappear, drastically reducing carbon production in stellar cores. Without abundant carbon, the foundation of organic chemistry and carbon-based life would be absent. The universe might remain sterile, despite containing vast numbers of stars and planets. The creation of other biologically important elements like oxygen, nitrogen, and phosphorus similarly depends on specific nuclear reactions with their own sensitivities to fundamental constants. Change these constants, and the elemental composition of the universe would shift, potentially eliminating key building blocks for complex chemistry and biology. The afterlives of stars, critical for dispersing these heavy elements throughout the cosmos, would also be affected. Supernova explosions, which seed interstellar space with elements forged in stellar cores, depend on particular neutrino interactions and nuclear processes that would be altered if physical constants changed. Without effective mechanisms to distribute heavy elements, planets might form from primordial hydrogen and helium alone, lacking the rocky materials needed for terrestrial worlds like Earth. The universe might contain vast numbers of gas giants, but few or no rocky planets with solid surfaces where complex chemistry could unfold. Planetary formation itself relies on a balance between gravitational attraction, which pulls material together, and various disruptive forces including stellar radiation pressure and the young star's magnetic field. Change the constants governing these forces, and the types of planetary systems that can form would shift, potentially eliminating Earth-like worlds entirely. Even if rocky planets could still form, their habitability would depend on maintaining liquid water on their surfaces for extended periods. This requires a delicate temperature range that depends on factors including the planet's distance from its star, the star's luminosity, and the greenhouse properties of the planet's atmosphere. All of these would be affected by changing physical constants. The development of complex life on Earth required not just suitable environmental conditions, but also protection from harmful cosmic radiation provided by our magnetic field and atmosphere. The strength of Earth's magnetic field depends on the movement of molten iron in our planet's outer core, a process sensitive to electromagnetic constants. Change these constants, and planets might lose this crucial protection, leaving their surfaces bathed in sterilizing radiation. Looking beyond individual planets to the cosmos as a whole, changing physical laws would alter the very fate of the universe. Current observations suggest our universe will continue expanding forever, gradually cooling to a state where no new stars form and existing stars burn out one by one. This heat death scenario depends on the current values of cosmological parameters. Different physical constants might lead to different cosmic fates. A more rapid acceleration could produce the Big Rip mentioned earlier. A cosmic deceleration could lead to the Big Crunch. Other exotic scenarios become possible with different parameter values, including oscillating universes that repeatedly expand and contract, or steady-state conditions where the cosmos achieves a kind of equilibrium. Perhaps the most profound cosmological consequence of changing physical laws would be the effect on information and causality. The structure of space-time itself depends on the constancy of the speed of light and the properties of gravitational waves. If these changed, the very fabric of reality would be rewoven. Light cones, which define the regions of spacetime that can be causally connected to a given event, would reshape if the speed of light varied. Information could potentially travel faster or slower than in our current universe, altering the fundamental limits on causality that constrain all physical processes. Black holes, those regions where gravity becomes so intense that nothing, not even light, can escape, would change their properties if constants shifted. The Schwarzschild radius, which defines the event horizon of a non-rotating black hole, is directly proportional to the mass of the black hole and the gravitational constant. Change g, and the size of black holes would scale accordingly. The process of Hawking radiation, through which black holes slowly evaporate by emitting particles, depends on quantum mechanical effects near the event horizon. This process would be affected by changes in quantum constants, potentially altering the ultimate fate of black holes and the information they contain. The way space and time relate to each other, encoded in Einstein's theories of relativity, depends critically on the constancy of the speed of light. If this constant changed, the conversion between space and time intervals would shift. Special relativity might need reformulation, and with it, our entire understanding of the space-time continuum. For conscious observers like ourselves, the cosmological consequences of changing physical laws would be profound. Our existence depends not just on local conditions suitable for biology, but on the entire cosmic history that led to the formation of our galaxy, solar system, and planet. Change the fundamental constants, and this history rewrites itself, potentially eliminating the possibility of observers like us altogether. Yet this sobering thought carries with it a fascinating implication. If physical laws can vary across time or space, regions might exist where different forms of complexity and consciousness could emerge, adapted to the particular constants operating in those domains. What we consider the fine-tuned conditions necessary for life might simply be the specific configuration that allows our form of life to exist. Other configurations might permit entirely different types of complex systems to develop, perhaps based on exotic chemistry, plasma dynamics, or forms of organization we cannot currently imagine. Consciousness might arise from substrates utterly unlike our carbon-based neural networks, perceiving and interpreting a universe operating under different fundamental principles. For now, these remain speculations at the frontier of cosmology and physical theory. But they highlight how deeply our existence is connected to the specific values of fundamental constants that shape our universe. They remind us that the cosmos we observe, with its galaxies, stars, and planets, is not the only possible configuration of reality, but one manifestation among many potential universes governed by different physical laws. In contemplating these cosmological consequences, we gain a deeper appreciation for the remarkable confluence of parameters that allows our universe to support complexity and consciousness. We recognize more clearly how the largest structures in the cosmos and the possibility of observers to contemplate them both depend on the precise tuning of fundamental constants that currently govern reality. As we near the conclusion of our exploration into changing physical laws, we must step back from the mathematics and physics to consider the deeper philosophical implications. What does it mean for our understanding of reality if the laws that govern it can change? How does the possibility of shifting fundamental constants reshape our conception of the universe and our place within it? These questions extend beyond physics into the domains of metaphysics, epistemology, and even theology. They challenge our most basic assumptions about the nature of reality and the foundations of knowledge itself. Let us begin with perhaps the most fundamental question: are physical laws discoveries or inventions? Do they exist independently in some abstract realm, waiting to be uncovered by human investigation? Or are they merely useful constructs, human-created models, that approximate patterns in our observations? The traditional scientific view has leaned toward the former, suggesting that laws of nature exist independently of human observers, governing the universe whether we understand them or not. In this Platonic perspective, mathematical truths and physical laws have an objective existence, a reality perhaps even more fundamental than the material world they describe. If physical laws can change, however, this view becomes more difficult to maintain. Laws that vary across time or space seem less like eternal truths, and more like contingent facts, descriptions of how things happen to be rather than how they must necessarily be. They become more like historical documentation than mathematical certainty. This leads to a second profound question. Are physical laws necessary or contingent? Could the universe have operated according to different rules, or are the laws we observe the only possible ones that could govern a coherent reality? If laws can change through cosmic evolution or vary across a multiverse, this suggests contingency rather than necessity. The specific values of constants like the speed of light or the gravitational constant would not be derivable from first principles alone, but would depend on cosmic history or location within a larger multiverse structure. This contingency creates space for what philosophers call modal realism, the idea that other possible worlds or universes with different physical laws might have equal claim to reality as our own. If physical laws represent just one possible configuration among many, then why does our universe operate according to its particular set of rules rather than others? The anthropic principle offers one response to this question. In its weak form, this principle simply notes that observers can only exist in regions of the universe or multiverse where physical laws allow for their existence. If constants can vary, we necessarily find ourselves in a realm where they take life-permitting values, regardless of whether such realms are common or rare in the larger cosmos. In its stronger forms, the anthropic principle suggests that the universe must have properties that allow conscious observers to exist. Some interpretations take this further, proposing that observation itself plays a role in determining the physical laws, creating a kind of cosmic feedback loop between consciousness and fundamental reality. These anthropic considerations connect to a third philosophical question. Are physical laws emergent or fundamental? Do they represent the deepest level of reality, or do they arise from something more basic? Traditional physics has assumed that laws are fundamental, the irreducible foundation upon which all complexity is built. But if laws can change, perhaps they emerge from deeper patterns or processes that we haven't yet understood. Just as the laws of thermodynamics emerge from the statistical behavior of countless particles, perhaps what we call fundamental physical laws emerge from deeper structures in reality. Some theoretical frameworks suggest that space-time itself might be emergent rather than fundamental, arising from networks of quantum entanglement or information relationships. If space and time emerge in this way, the laws that govern them might similarly be emergent, patterns that crystallize from more fundamental processes rather than absolute rules imposed from outside. This perspective aligns with certain interpretations of quantum mechanics, particularly those that emphasize information and relational properties. In these views, reality is not ultimately about substances and forces, but about relationships and information exchange. Physical laws would then represent stable patterns in these relationships, rather than externally imposed rules. A fourth philosophical question concerns the relationship between mathematics and physical reality. Why is mathematics so unreasonably effective at describing the physical world, as physicist Eugene Wigner famously wondered? And what happens to this relationship if physical laws can change? If mathematical relationships are necessary truths, while physical laws are contingent, then the match between mathematics and physics becomes more mysterious. Why should contingent physical reality conform to necessary mathematical patterns at all? And if physical laws can change, does this imply that different mathematical structures become relevant in different cosmic regimes? Some philosophers and theoretical physicists have proposed that reality is fundamentally mathematical in nature, that physical objects and their relations are actually mathematical structures. This mathematical universe hypothesis suggests that physics doesn't just use mathematics as a tool, but actually studies mathematical structures directly. If this view is correct, then changing physical laws might represent transitions between different mathematical structures or different solutions to underlying mathematical equations. The multiverse would be a kind of mathematical landscape, with different regions corresponding to different stable configurations or solutions. These considerations lead to a fifth philosophical question. What is the status of time in a universe where physical laws can change? Does time exist at a more fundamental level than physical law, providing the backdrop against which laws evolve? Or are our notions of time themselves emergent from physical processes that might operate differently under different physical regimes? The relationship between time and physical law becomes particularly puzzling when we consider vacuum decay scenarios. If a bubble of true vacuum expands through space, replacing our current physical laws with different ones, what happens to the continuity of time across this boundary? Could an observer somehow exist on both sides of such a transition, experiencing the shift in physical law as a temporal event? Some theoretical frameworks, like the block universe interpretation of relativity, suggest that time itself is not fundamental, but emerges from the structure of four-dimensional space-time. If physical laws can change, perhaps the block universe itself transforms, with different regions operating according to different principles, but still forming part of a larger coherent structure. A sixth philosophical question concerns consciousness and its relationship to physical law. If consciousness emerges from physical processes governed by specific laws, what happens to consciousness if those laws change? Could awareness persist through a transition in physical law, or would it necessarily be extinguished and potentially re-emerge in new forms? The hard problem of consciousness, understanding how physical processes give rise to subjective experience, becomes even harder when we consider changing physical laws. If consciousness depends on specific physical configurations like our carbon-based neural networks, then changing laws would likely eliminate consciousness entirely if they no longer supported such structures. But if consciousness is more fundamental, perhaps related to information processing or integration in a way that transcends specific physical implementations, then it might potentially adapt to different physical regimes. Consciousness might be more flexible than we imagine, capable of emerging through different physical substrates operating under different fundamental laws. Some philosophers have even suggested panpsychism, the view that consciousness or proto-consciousness might be a fundamental feature of reality, present in some form at all levels of existence. If true, consciousness might persist through transitions in physical law, though its specific character and capacities would likely transform dramatically. A seventh philosophical question concerns values and ethics in a universe of changing laws. If physical reality itself can fundamentally change, what implications does this have for moral reasoning and value systems? Are there ethical principles that would remain valid across different physical regimes? Or are our ethical intuitions inseparably tied to our specific physical context? The possibility of changing physical laws challenges us to distinguish between contingent values rooted in our particular physical environment and potentially universal principles that might transcend specific physical implementations. It invites us to consider whether consciousness, regardless of its physical substrate, has inherent value that would remain meaningful even in radically different physical contexts. This connects to an eighth philosophical question about meaning and purpose in a mutable cosmos. Many religious and philosophical traditions have found meaning in the apparent constancy of natural law, interpreting the universe's order as evidence of divine design or cosmic purpose. How might these perspectives adapt to the possibility that such order is temporary or local rather than eternal and universal? For some, the possibility of changing physical laws might strengthen rather than weaken religious interpretations. A cosmos that evolves not just in its contents, but in its fundamental principles, might better align with theological conceptions of ongoing creation or divine immanence than a static, clockwork universe operating according to unchanging rules. For others, the contingency of physical law might suggest a universe without inherent purpose, where meaning is created rather than discovered by conscious beings. In this view, the recognition that even the deepest structures of reality might be impermanent invites us to embrace the present cosmic configuration while acknowledging its transience. A ninth philosophical question concerns predictability and determinism. Classical physics presented a deterministic universe where complete knowledge of the present state would allow perfect prediction of all future states. Quantum mechanics introduced fundamental uncertainty, but still within the framework of unchanging physical laws that govern probability distributions. If physical laws themselves can change, predictability becomes even more limited. Even a hypothetical perfect observer with complete knowledge of the current state of the universe could not predict its future if the rules governing its evolution might themselves shift unpredictably. This has implications for how we understand causality itself. If the relationship between causes and effects depends on specific physical laws, what happens to causation during transitions between different legal regimes? Can we meaningfully speak of causes and effects that span such transitions? Or does causality break down at these boundaries? A 10th and final philosophical question concerns the limits of human understanding. Can we truly comprehend a universe whose fundamental principles might change? Our cognitive architecture has evolved within a specific set of physical laws and is adapted to understand phenomena governed by those laws. Our mathematics, logic, and conceptual frameworks all reflect this adaptation. If physical laws can change dramatically, we may encounter fundamental limits to our ability to model or predict such changes. The tools of mathematics and logic that serve us so well in our current physical regime might prove inadequate for understanding transitions to entirely different regimes that operate according to principles we can barely conceive. This suggests a profound epistemological humility. Even as we develop increasingly sophisticated theories of physics that might accommodate changing fundamental constants, we should recognize that our understanding remains rooted in our specific cosmic context. Our knowledge is situated, rather than absolute, powerful within its domain, but potentially limited when confronting radical alterations to reality's basic structure. Yet this recognition need not lead to despair or radical skepticism. The very fact that we can conceptualize changing physical laws, even if imperfectly, demonstrates the remarkable flexibility of human understanding. Our ability to use mathematics and logic to model phenomena far beyond our direct experience suggests that cognition can transcend its evolutionary origins to glimpse deeper patterns in reality. Perhaps consciousness itself, whether human or alien, quantum or classical, carbon-based or silicon-based, represents a cosmos coming to know itself through myriad forms across different possible physical regimes. Each form of awareness might grasp different aspects of reality, limited by its specific physical implementation, yet participating in a larger cosmic exploration of possibility. In this view, our philosophical reflections on changing physical laws aren't merely abstract speculations, but part of the universe's ongoing inquiry into its own nature and potential. Through the evolution of consciousness in its many forms, the cosmos might explore not just what is, but what could be, including radical transformations of its own fundamental principles. As we conclude these philosophical reflections, we return to where we began, with wonder at the remarkable confluence of physical laws that allows us to exist and wonder at all. Whatever their ultimate nature, whatever their past or future variations, the physical laws we observe have conspired to create a cosmos capable of contemplating itself through minds like our own. This capacity for self-reflection, for asking these deep questions about the nature of reality and our place within it, represents one of the most extraordinary features of our universe. Whether physical laws are discovered or invented, necessary or contingent, fundamental or emergent, they have somehow given rise to beings that can ponder these very questions. In that pondering, in the philosophical journey itself, we find meaning regardless of whether physical laws are eternal or ephemeral. Through our quest to understand reality's deepest structures, we participate in the cosmos coming to know itself, even if that self-knowledge remains partial, evolving, and ultimately transformable. As our journey through the cosmic landscape of changing physical laws draws to a close, we find ourselves returning to the stars, to the silent depths between galaxies, to the humbling vastness that cradles our small blue world. We have ventured far into theoretical realms, contemplating how reality itself might transform if its fundamental rules were to shift. Now, in these final moments together, let us gather these threads into a tapestry of wonder and perspective. We began by questioning what seemed unquestionable, the constancy of physical law itself. We asked whether the speed of light, the gravitational constant, the fine structure constant, and other fundamental parameters might have been different in the distant past, or might change in the future. We explored evidence suggesting subtle variations in these constants across cosmic time and space, tantalizing hints that reality might be even more dynamic than we previously imagined. We've considered how alterations in gravity would reshape celestial architecture, sending planets spiraling into their suns or drifting away into frozen darkness. We've envisioned stars burning fiercer or dimmer as electromagnetic forces strengthened or weakened. We've contemplated particles gaining or losing mass, transforming the very building blocks of matter. We've examined the possibility of vacuum decay, that existentially unsettling scenario where a bubble of altered physics expands at light speed, rewriting the fundamental rules across an ever-growing region of space. We've pondered cosmic phase transitions where the universe shifts from one set of operating principles to another, much as water transforms to ice when temperatures fall. In these explorations, we've discovered something profound. The universe we know, with its galaxies and stars, its planets and living things, its possibility for consciousness and contemplation, depends on an extraordinarily precise configuration of physical laws. Change any one parameter significantly, and the cosmic story unfolds differently, perhaps without the characters capable of reading that story at all. This apparent fine-tuning has led some to see evidence of purpose or design in our physical laws, a cosmic architect who calibrated the constants precisely to allow for life and mind. Others find in it support for a vast multiverse, where regions with different physical laws proliferate endlessly, and we necessarily find ourselves in one of the rare patches where consciousness can emerge. Still, others seek deeper principles that might explain why physical laws take the values they do, suggesting that what appears arbitrary might actually be necessary. Whichever interpretation we favor, the delicate balance of our cosmic parameters invites both gratitude and humility. We exist in a universe that, at least for now, maintains physical laws compatible with complexity, chemistry, biology, and thought. Whether by design, chance, or necessity, we find ourselves in a moment of cosmic history where the fundamental constants allow for conscious beings to evolve and wonder about those very constants. Yet our exploration has revealed that this stability may be temporary. Theoretical physics suggests mechanisms by which fundamental constants might drift slowly over eons or change suddenly through cosmic phase transitions. The eternal laws we once took for granted may be more like weather patterns in a deeper cosmic climate, stable for a time but ultimately changeable. This perspective transforms our relationship with physical law. Rather than seeing ourselves as temporary beings in an eternal framework, we might recognize that the framework itself could be transient. The stage and the players might both be participants in a larger cosmic evolution, where not just the contents of the universe, but its fundamental character develops and changes. Such flux need not diminish the wonder of existence. Indeed, it might deepen it. If the specific configuration of physical laws that allows for our existence represents just one arrangement among countless possibilities, then the confluence of parameters that permits consciousness becomes all the more remarkable. The universe's capacity to explore different possible rule sets through cosmic evolution reveals a creativity at the heart of nature that extends beyond the emergence of life to the emergence of physical law itself. For conscious observers like ourselves, contemplating changing physical laws challenges us to distinguish between the contingent and the necessary in our understanding of reality. Some aspects of our physics might be accidental features of our particular cosmic patch, while others might represent deeper principles that would persist across different physical regimes or emerge repeatedly in various forms. This suggests a research program for theoretical physics, identifying which features of our current physical theories are likely to be universal across different possible rule sets and which might be specific to our particular cosmic configuration. Such an investigation might reveal meta-laws that govern how physical laws themselves can change, principles that constrain the space of possible physics, even as they allow for variation within that space. For philosophers, changing physical laws invite a reconsideration of the relationship between mathematics, physical reality, and consciousness. If physical laws can vary while mathematical truths remain constant, what does this tell us about the foundations of reality? If consciousness can potentially arise in different physical regimes through different substrates, what does this suggest about the nature of mind and its relationship to matter? For those of a spiritual inclination, the possibility of changing physical laws might open new ways of thinking about ultimate reality. The divine might be conceived not as the architect of an unchanging cosmic mechanism, but as the wellspring of an evolving, creative universe that explores its own potential through successive transformations of its fundamental character. The cosmos becomes not a finished creation, but an ongoing creative process. For all of us, regardless of our metaphysical commitments, contemplating changing physical laws offers an expansion of perspective. We recognize more clearly the remarkable confluence of factors that allows us to exist, the precise balance of forces that permits atoms to form, stars to shine, planets to orbit, and life to emerge. We see our moment in cosmic history as precious and perhaps rare, a window of opportunity where the physical laws allow for beings like us to evolve and contemplate the cosmos. This perspective might foster a deeper appreciation for our brief moment of consciousness within the vast cosmic drama. If physical laws themselves can change, then the specific configuration that allows for our existence might be fleeting on cosmic timescales. Our window for observation and understanding might be limited not just by the biological constraints of our species, but by the potential impermanence of the physical regime that makes our form of life possible. Yet rather than despair at this potential transience, we might find in it an invitation to wonder more deeply at the present moment. The constants of nature have remained stable long enough for stars to form, planets to cool, and consciousness to emerge and contemplate its own origins. Whatever the future may hold, whatever transitions physical law might undergo in the deep cosmic future, we exist now, within a set of physical parameters that allows us to observe, understand, and appreciate the remarkable universe that surrounds and constitutes us. If the laws of physics shift, so does everything we know. The foundations of reality itself would transform, creating perhaps a cosmos where different forms of complexity and consciousness might eventually emerge, operating according to principles we can barely imagine from our current perspective. Yet in this moment, under these physical laws, we find ourselves capable of pondering such possibilities, of using mathematics and language to glimpse realities beyond our direct experience. This capacity for transcendence, for reaching beyond the immediately given to contemplate what might be or might have been, represents one of the most extraordinary features of consciousness. Through science, philosophy, art, and contemplation, we extend beyond our specific cosmic location to imagine different possibilities, different configurations, different laws. We cannot change the physical constants, but we can explore their implications through thought, suggesting a capacity in consciousness to partially liberate itself from the specific physical regime in which it emerges. As we conclude our journey together, we return to the night sky, to the stars whose steady light travels across vast distances according to the laws we have been contemplating. Their apparent constancy reassures us while simultaneously connecting us to the deepest questions about the nature of reality. In their ancient light, we read the story of our cosmos, a universe apparently stable in its laws, yet perhaps harboring the potential for profound transformation. Sleep now, held in the arms of a universe in flux. Rest in the temporary cradle of physical law that makes your existence possible. Dream perhaps of other possible physics, other configurations of reality, other ways the cosmic story might unfold. And when you wake, look with fresh wonder at the world around you, recognizing in its familiar patterns the extraordinary confluence of physical laws that allows you to see and know and wonder at all. In the ever-changing dance of existence, we find the endless poetry of the cosmos, a universe coming to know itself through beings capable of questioning its deepest nature. Whether physical laws are constant or mutable, necessary or contingent, discovered or invented, they have conspired to create this moment of awareness, this brief window of consciousness peering out at the stars and inward at its own nature, unified in a grand cosmic exploration of possibility.